title.
Okay. Hi, everyone. My name is Igor Konnov. I'm a principal scientist or researcher, I never remember, at Informal Systems. And I'm going to tell you about TLA Plus and Apalache, how they help us in developing specifications and protocols at Informal Systems. Before I tell you this interesting story, I have to put this warning. That's what the Ministry of Chaos Engineering asked me to do. This talk contains propaganda of TLA Plus. Many users are known to develop symptoms of precise thinking after regular use of TLA Plus. And this is known as thinking above the code, as discovered by Dr. Lampert. To reduce the effects of this addiction, TLA syntax was diluted with backslashes and other unusual symbols. End of warning. So in the rest of this talk, I'm going to talk a bit about the Tendermint Light Client, about how we write specifications in TLA Plus without going into many details. And I'd also give you an idea how the Apalache model checker is helping us in exploring these specifications and the protocols. But before we start talking about TLA Plus, I want to address the common concern. Many people say, I actually don't need to write specifications. I have code, and that's what I need. That's the ultimate truth. And here I want to tell you that you actually have been writing specifications for quite some time without even knowing about it. For instance, look at this piece of English text, which is saying that denominations can be from 3 to 128 characters long and support letters followed by either a letter, a number, or a separator slash. That's actually an English specification, and I just found it in the Cosmos SDK. On the right-hand side, you can see an implementation of this specification. That's what I did myself. It's not actually part of Cosmos SDK. You see it's a bit of code here. If you think about it, you'll probably see that it matches the English specification. And on the left-hand side, you see a regular expression. That's actually a formal specification. What it tells you that you have English letters, capital letters and small letters, and then digits, slashes, and how many of them you can have. So you see, you actually are doing these things. Just in case of regular expressions, you can automatically synthesize the code that recognizes a string matching a regular expression. But actually, these regular expressions are a formal language. So what's good about these three different things? The English specs are actually quite easy to understand. However, they're ambiguous. When the English spec is saying that denominations can support letters, I might think they also can support Russian letters or maybe Chinese symbols, and you probably think they only can contain English letters. We don't know. They're ambiguous. They're also non-executable unless somebody invents a very powerful AI in the next 10 years. But before that, we have to live with formal specs. What's good about implementations? So implementations are what we do. That's how we do things. They're ultimate truth. We like them. They're unambiguous because they're going to be executed on your computer or other computers. And of course, they're executable. What about formal specifications? That's what we want to see, not how we want things to be done. They're actually concise. In this case, this specification is very concise, right? It's unambiguous, and sometimes it's even executable, right? So I just want to tell you that you have been writing some specifications. And when you actually write types, for instance, in Rust, you also kind of write some specifications, and the type checker is doing some form of proofs. So I would just tell you to think about what you do and how useful specifications can be. Okay, so let's talk about TLA. And before we talk about it and before we talk about the Light Client, I want to ask you a question. What is your protocol? There are many phases of a protocol. What do you understand by a protocol? And what we do at Informal, we actually have 4 kinds of activities. And they all reflect different phases of a protocol, for instance, the Light Client protocol. Of course, we always start with an intuition. Somebody writes the ideas on a whiteboard, like sequence diagrams, or maybe somebody explains how things work in a Zoom meeting. Then we write an English specification, and from that we actually write a TLA specification and trust code or Golang code. So these are different things, different artifacts and different activities. What we do about English and TLA specs, we do peer review. We see whether English specs and TLA specs match each other, and the same we do about the code. We check whether the Rust code is matching the English spec or the other way around. And as you have probably seen in the previous talk yesterday, the talk by Andrei Kupriyanov, we can also do model-based testing. We can generate tests from TLA specifications for Rust code or Golang code, so we can see that the things stay in sync. So let's talk about the intuition a bit. You probably know all of this. I just want to remind you a bit about what blockchain in Tendermint is and how the Light Client is supposed to operate. So a blockchain is simply a sequence of blocks. They have some fields, they have heights, time, the validator sets, next validator sets, and each block also contains the set of commits for the previous block. Right? There are also hashes, but let's not go further into that. What's important here is that a commit for the previous block actually contains more than 2/3 of signatures signed by the validators from the previous block. That's a very important assumption. Then, if I have a Light Client, I start with some root of trust. I have some block, and I just got it from somewhere. For instance, I could get it from Jarko or Ethan, and I just trust them that this block is correct. Then, if I want to get a block which is further away from the trusted block, what do? I ask a peer node for a new block and download it. But can I trust this new block? Of course not, because there can be Byzantine processes, validators, and I have to figure out whether this block is actually correct or not. How do I check that the block is actually coming from the chain? For instance, if I trust block 1 and I need block 9, what do? In this case, I have to look at the commit, say, for block 9, and for that I'll have also to download block 10, which contains the commit for the block 9. And then I have to check that this commit contains a signature of at least one correct validator. What does it mean? Now we have to understand what it means for a commit to contain a signature by at least one correct validator. And now we have to look at this Tendermint security model, which is quite complex if you think about it. Now we have to understand that faulty validators have less than 1/3 of the voting power, that there is a trusting period which tells us that we can trust block 1 within several weeks or several days. And we know that if we miss the trusting period, then we cannot trust anything signed by the validators in the trusted block. What's important here is that we want to see whether we have more than or at least 1/3 of the signatures from the validators in block 1. So that's intuition. We can go further and further, but that's getting more and more complex. So you need somebody to explain you how these things work. And usually you need some guru, like here in the picture, who knows this protocol pretty well. And this guru can just tell you how things work, give you some scenarios and so on, so forth, right? But what happens if your guru is sick or just went on a silent meditation? Well, you have a problem. You have to find another guru. Or maybe you should use an English specification. That's another thing that we are doing. So in an English specification, we are trying to capture a protocol at a high level, more or less at a mathematical level, but without going into too many details. We start with a sequential statement of a problem. Like if you had a sequential algorithm, then we transform it into a distributed problem. And more importantly, we also specify what kind of properties do we expect from the protocol. Say we expect some safety properties, for instance, that the agreement is never violated, and some liveness properties, for instance, that all validators will eventually decide on some value on some transactions. What we do there, we also decompose the protocol into smaller functions and give pre and post conditions of the happy path, what happens actually if everything goes well. And also importantly, we give the error conditions. We describe the unhappy path, what should happen if things do not work well. What's good about it, it's actually given us a good understanding of the protocol and its properties. And what's also important here is that it's kind of straightforward to write a TLA specification following this English specification. Of course, for that, you need the guidance of this guru and the person who wrote the English specification. So I'm not telling you how, I'm not giving you the details of writing the specs. You can go on the GitHub and see for yourself how these specifications look like. So now we have the guru who has the intuition. Now we have another person who can write English specs. And it looks okay. However, it's also a bit complicated because writing English specifications is hard. You really need somebody who is well-versed, who can write these texts unambiguously without too many problems. Because if you just sit down and write an English specification, you and me can understand them differently. It's a very important skill how to write these specs in a precise way. So now we come to the TLA specs. I'm not going to give you an introduction to TLA Plus, just give you some ideas because well, I cannot give you a new language in basically 5 to 10 minutes. What I want to give you, an example of how we specify the blockchain for the Light Client protocol in TLA Plus. And for that, I'm giving you not a full detailed specification of the blockchain. I give you something like a minimal viable model. So the thing which is small enough, which has all important constraints and properties for the Light Client protocol, but it doesn't go into implementation details. So let's start. It will take us a few slides. I promise we are not going to do anything very complex. So what is a block? A block is a record that has height, time, validator set, next validator set, and commit. And I just say that commit is a set of validators. In reality, it's of course a set of pre-votes and pre-commits, but it's not important for the Light Client protocol. So I just say it's a set of validators. And the other fields I just ignore because they're not important for this protocol. So what do we do in TLA Plus? We introduce a variable, the blockchain, which kind of stores the global view of the blockchain, some kind of ideal blockchain, right? And how do we initialize? How we initialize our system? How do we initialize this blockchain? So we assign the blockchain this value. It's basically a sequence that contains a single record, and this record has a number of fields that are exactly the fields you have seen before. So we have the height of 1, time which is equal to 0. The validator set is a set of strings, and these strings are just names that I have given to the validators. I'm not giving public keys here because I don't care. It's not important for this specification that we have public keys. I just want to distinguish between different validators. Then I have the next validator set, which I just give you in a second. And we have the last commit, which is empty in the Genesis block. We could assign some other value. So how do we assign the next validator set? In reality, it depends on your application. But what I can say is that I have an nondeterministic choice. I just pick some next validator set. And that's where the power of TLA Plus is shown. You just can write that there exists some NVS for the next validator set, which is a subset of this set of validators, N1, N2, N3, and N4. And this is what I put into the next VS field here in this record. So what's important here, I don't want to fix a specific decision of how you choose the next validator set. It depends on the application. That's why I just say pick some. And we also want to introduce faulty processes because we are writing a specification. So we can explicitly keep track of who's faulty and who's not. Right. So here we assign faulty to be an empty set in the initial state, and we will change it later. So it looks like that. We also have to add these two mounting symbols, which are actually conjunctions or AND operator. And there is this kind of syntactic agreement in TLA Plus that you can group these formulas by using indentation. What's important here is that you have 6 initial configurations due to non-determinism that we have introduced here. So this spec is not describing a concrete execution. It describes basically 16 initial states that can proceed further to other states. Okay, that's all about initialization. How do we? Oh, not all. So if you wondered why do I have 4 validator sets, I can actually have more. I can introduce a constant of all nodes, and whenever I want to run the model checker, I can actually initialize this constant with a value I like that has 4 validators, or maybe 10 or 100. So there is a way to get rid of constants, if you like, of literals, right? So you can introduce constants. What about transitions? To introduce transitions, we have to write this next predicate, and basically we write this symbol character V, which means or a disjunction. And here we are saying that we basically can have 2 different transitions, and we choose between them non-deterministically. Here I give you an example of the transition that introduces one more fault. Basically, again, I'm saying I don't know how the nodes can fail. I just have no clue. I don't care, right? What I'm saying here is that I just pick a node from the set of nodes that is not faulty yet. And all nodes / faulty means set difference. So I just subtract faulty from all nodes and pick some n from this set. And then I assign this new set of faulty nodes to faulty prime that will pick the value of faulty in the next state after the transition. And I say the blockchain hasn't changed. What's important here, we again have non-deterministic choice. You can choose between 2 different transitions depending on whether they're possible or not. Okay, so now we want to add a block. That's a bit complicated. You don't have to understand all of it, but there is not so much happening here. We just take the last block. We non-deterministically choose the next timestamp again. We non-deterministically choose the next validator set and the set of commits. And then we construct this block. We say that its height is 1 plus the length of the blockchain. The timestamp is exactly as I chose here with existential operator. And I assign the validator set to be exactly the set of next validators. And the next validators in this block I have chosen non-deterministically. And last commit is also non-deterministically chosen. What's important is that I cannot just pick an arbitrary block. I have to put some constraints, as we discussed in the intuitive picture. Here I'm saying that the time is growing monotonically, that my new block is not too far away from the last block, so there must be the tracing period in the picture. And also important that there was more than 2/3 of validators who have voted on the last commit. And this I can express with these cardinality expressions in TLA+. So there is no magic, it's just some weird, maybe weirdly looking code, but in the end, it's actually a lot of constraints which look a lot like a programming language. What's important here is that we have these non-deterministic choices, because when you make this existential quantifier and then later assign something to the variable, you basically say, I don't know how you do it, you just choose some values, and if they don't satisfy my constraints, you choose other values. So basically, if you wondered what a non-deterministic machine is, basically TLA is giving you a non-deterministic machine. Okay, so how is it better than English? It's just a lot of formulas, a lot of constraints. One thing is that, of course, we can parse this specification, and we can do very stupid mistakes that we can do in English. But what's also important is that Apalache, the model checker, or TLC, another model checker, it can fill the gaps in our understanding about specifications. For instance, I can just hypothesize that, for instance, for all the blocks in the blockchain, less than a third of validators in every block is faulty. And if you write it in English spec, nobody is going to tell you that it's not true, except your reviewers. If you're lucky, they find this problem. But if you run the model checker, it will tell you very quickly that there is a violation execution. So it will show you a counterexample that kind of refines your understanding of how the protocol is working. It's not necessarily showing that your specification is wrong. It might be correct. Just your lemmas, your invariants that you expected to hold true, they don't hold true. So that's quite useful. It actually helps us to learn a lot about the protocol just by running the model checker, by experimenting with the model checker, and trying different properties which you sometimes believe are correct, and they're not. So if you want to use TLA Plus, somebody might tell you have to run the TLA Toolbox because it's a standard tool, but you actually don't have to do that. What I'm doing usually, I'm running Vim as a text editor, and I'm running Apalache or TLC in the command line in the terminal. So it's actually quite lightweight. You just have to understand the language. You don't have to use very powerful IDEs to do the things. So I'm not giving you the details of the Light Client specification. You can check it on the GitHub again, because it would just take too much time. What's essential here, we have the specification of the blockchain. And this specification is very close to what I have just shown you. And then we have a specification of the skipping verification that does bisection. I didn't go into details. In the intuitive picture, I'm not going in details here. It's quite a reasonable specification, just 850 lines of code. So I find it quite readable. It has 15 invariants. Some of them hold true, some of them don't hold true, but that helps us to understand what kind of assumptions actually work and what do not work. What's important, we checked the specification with Apalache for small parameters like 4 to 7 validators, 3 to 7 blocks. Apalache was able to do that within minutes, so we got very quick feedback. Unfortunately, we cannot do it for like 100 validators because there is a combinatorial explosion even in symbolic model checkers. But what's important here, we see the mechanics of the executions, we see how things work, at least for reasonable small numbers. And we also have found some non-obvious properties that do not hold true. They are not violations of the protocol, because if you ask your guru, he will tell or she will tell you that these properties were not supposed to hold. But I was quite surprised to see them. For instance, it's possible that the Light Client reports OK to you, but then the collected blocks cannot be verified. Why is it so? Because the trusting period of the trusted block is over, and the model checker will show you exactly this counterexample. I'm just giving you this invariant here. You can go and check the specification. Another example, the Light Client is retrieving different blocks, and I kind of expected that if the Light Client is saying they're all OK, the Light Client said that it can trust a last block based on the trusted block, then all the intermediate blocks should be verified. But that's also not true, because the skipping verification can actually skip some of these blocks just because it has found some arguments to trust further blocks in this sequence. So the model checker and the TLA specifications, they help to refine our thinking. It's not the only spec that we have written in this year 2020. We actually have a number of specs delivered already. So that's Light Client verification, Light Client detector, attack isolation, Tendermint safety, fasting, and several specifications for IBC that refine again thinking about how the protocol and its parts, its components should behave. So now we have this complete picture. I'm not going to tell you how to write code. You know it better than me. Now we have this complete picture. We have a guru who has intuition. We have an English spec written by somebody who can write English specifications precisely without too much ambiguity. We have a TLA spec, and that's a bit of an art because you have to think about constraints, you have to think about logic, and you have to try to keep these specifications as minimal as possible. And of course, you have the developers who use all of these things, and they try to synchronize all of these artifacts. And I'm not telling you that TLA is better than all of these other activities. I'm not telling you that you should replace developers with TLA specifications. That's ridiculous because the implementations are much more efficient than whatever we could ever generate from a TLA specification. So all these things belong together, all these people belong together, and they are acting as a team in producing these different artifacts. Okay, now these guys come again, and they say think responsibly. What does it mean? It means you have to write specifications and check them. I think they have a point. So I just want to wrap up here, and if you are at some point are just stuck with your pseudocode, if you are stuck with a whiteboard and you don't understand how the algorithm is operating, how your protocol is operating, if you have this issue, as I sometimes have, that you think something's wrong about the protocol, one way to do it without implementing the whole protocol is to write it in TLA+. So for instance, you go to the Apalache page, or you can go to the page by Leslie Lampert. You can check what we are doing, our specifications. You can check the video lectures on TLA+. And you can also join Apalache Zulip stream. I actually want to know what your opinion about all these things is. If you can give us feedback, that would be brilliant. We want to see if you want to write specs and what problems you have if you try to write specs. So that ends my talk, and now I will switch to questions, if there are any. Okay. Okay, so the question is saying you can ask questions here. Is it a starship on the wall? Yes, there are several of them. This one is Millennium Falcon, and there are different fighters like X-Wing and other things. It looks a bit lively when I have these blueprints here. All these are not real starships. Good. So if you don't have a lot of questions, I have questions for you. Let me see. So let me just turn this on. When you see it. So I was really wondering why people don't write specifications, say in TLA or other formal methods, other formal languages. So, of course, there are several standard answers, right? First of all, I'm too busy writing my code, but then at some point you have to test it. Another one is I don't need tests, my code is perfect. I haven't heard this answer for some time, but maybe some people think it. How many tests do you actually write? And I think another problem is that some people are just afraid of finding the bugs in the protocols. I'm afraid of finding bugs in my code. So if you feel like that, I would like to hear it and to learn more about it. You could write to us in the Zulip stream. And of course, there are more practical questions like, I just don't like the TLA syntax. You can actually change it if you don't like it. You can write a translator from another language to TLA, for instance. Or maybe you're just lacking some resources on TLA+. You could write a tutorial. And last but not least, is that maybe you just want to execute TLA without running the model checker. we can try to do that. Aha. Right. So, So too much time is spent tweaking specifications versus writing code. At some point, it's better to start laying down code. Well, I agree. So one thing is that if you are writing specifications in the specialized languages, for instance, if you want to use a specialized model checker, it's quite hard to write a specification that fits into the fragment of the model checker. That's a very painful experience. So for TLA Plus, it's actually quite different. It's a very general language that makes the model checker suffer, not you suffer, right? So for you, it should be easier to write the specification. For the model checker, it will be harder to check your specification. We could define a specialized language which would be much easier to verify, but we feel actually that the plus of the TLA Plus is that you don't have to think too much about how you write down your specifications. And of course, it's easier to write code in many cases. I do agree with that. I'm also not writing TLA specs for our model checker. However, if you write thousands of lines of code, like hundreds of thousands of lines of code, somebody who joins the project has to read them. And that is a big painful moment, right? So somebody has to walk through, the newcomer, walk through this code, explain the hard parts. You have to spend a lot of time. The specifications is kind of easier. They're much shorter. They contain the important parts, the essential parts, and they don't contain all the implementation details. So there is a value in specifications in the long term. If you just want to hack a project, I would also sit down and write a prototype. But then if you want to have long-term consequences, I think you need specifications.
Cool. Thanks, Igor. This was a really great talk. We're going to transition to our next session now.
Thanks a lot.
Cool. Thanks again.